go. We are recording now. It is February 18, 9:42 a.m. Pacific Standard Time. And let's take a look at our syllabus first. That's the syllabus here. Okay, we have, go. We are writing here. Let's highlight that. Okay, we are going to lecture for 1 hour, and then we do our so-called lab. If you don't have a lab group, let me know. Okay, understand most of you got your book, got your group, right? Your group, your team partner.
Yes.
Okay, good. And so let's get here. If you don't have a lab partner, let me know, and I will assign you to someone. Okay, and that's Chris, right? Chris doesn't have a group partner. Okay. Okay, we'll get there, Chris. Anybody else in addition to Chris? Okay, Juan Torres Arellano. Okay, so you might want to join forces with Chris, okay, since he doesn't have a partner. So why don't you exchange contact, Chris and Juan? And you can be in the same group. Let's see where we stopped last time. Okay, I was talking about what we have covered so far, right? Electric charge versus mass, electric force versus gravitational force, electric field versus acceleration. We talked about the electric force. Now we're going to talk about the electric field. We need to know what the electric field is so we can understand today's lab. We also need to know about the electrical potential energy and the electrical potential for today's lab. That's where we left last time. Today is February 18th, 2026, Wednesday. I'm adjusting here the paragraph, and I'm going to read also the illustrations. That's in my PowerPoint. Electric charge. Okay. Let's see if there is something that we didn't cover. Electric charge and forces. Yeah, here you go. Here are some qualitative examples, right, of the electric force. The electric force is a vectorial force. So whenever you have a single electric charge being subjected to the force from multiple charges, the net force applied to this electric charge is going to be the vectorial summation of the force. So the electric force behaves just like our regular mechanical forces. That's what you have to know, okay? This vectorial resultant has a name. This process of getting the forces summed vectorially has a name. It's called the principle of superposition. Okay, so multiple charges acting. Let's see, and it's not acting, but interacting. Okay, interacting with a single one, comma, result in multiple electric forces that sum vectorially with each other. Okay, this is the same principle we saw in mechanics. In physics, no? In physics 06. Let it be, right? This vectorial summation as a name is called it's a principle. Is called the superposition principle. So we also use, recall that we also use the superposition principle in physics 06. And it's called, it is called the superposition principle. That's what we have right here. One example. Okay. So mathematically, right? Let's put that mathematically speaking, right? So consider, for instance, 4 charges next to each other. The net force acting in charge number 1, the net electric force, right? Electric force acting in charge number 1 is going to be given by the superposition principle. The net force, superposition principle. Here we go. And now I'm going to insert my equation right here. Here we go. Net force, comma, 1. No, it doesn't like it. Net force in charge number 1. And I have to put a vectorial symbol here, right? Here you go. I have to put a vectorial symbol, otherwise it's going to be given by the force that charges 2 apply to charge 1. I'm going to take out the comma, okay, to simplify my notation. Charge 3 applies to charge 1, and charge 4 applies to charge 1. That's what's going to be the net force. And that's, again, is a vector. And now that we talked about the net force and the superposition principle, okay, We can also talk about electrical conductors before we go into the electric field. Okay, let's talk about electric conductors. Electric conductors and insulators. Okay, remember that in physics 6, we also have thermal conductors and thermal insulators, right? It's the same idea. It's exactly the same idea that we had before. Electrical conductors, let's see. Electrical conductors allow electric charges to move freely inside it. Electrical insulators is the opposite. Electrical insulators, an electrical insulator behaves in the opposite way, right? An electric insulator behaves in the opposite way. So just think about the wiring at home. Just think about the wiring at home. Okay, and how does it apply to thermal conductors and thermal insulators? Same thing, okay? Versus, let's see, versus thermal conductors and thermal insulators. Electrical conductors, insulators, electrical slash thermal conductors allow not just electric charge, but heat, right? Electric charge is like slash heat to move freely inside it. An electric slash thermal insulator behaves in the opposite way. Okay, just think about the wiring at home. What is the material? What is the material that you use in the wire? The core. Let me even specific here. What's the core material that you use in the wiring at home? At home, right? The core material. I'm being very specific here. What's the core material? I'm gonna emphasize here. That's using wiring at home, right? If you have opened the wiring there, do you use a plastic inside your wiring? Yes or no? Do you use a plastic material inside your wiring? Huh? Anybody can answer me that? Do you use a glass? Do you use a glass material inside the wiring? Anybody can answer me that? Huh? Well, which other material can talk about? Do you use a paper? Let's see. Inside the wiring, you have like a cylinder, right? A fiber. The wire is a fiber, right? You have a fiber. And the fiber, what's the material that the fiber is made of, right? What is the material that the wire slash fiber is made of? It's made of, right? If you're familiar with that, if you're familiar with electricity, you would know. If you're familiar familiar with electricity, you would know that the electrical wiring is made of most of it, right? That most electrical wire, is made of copper. Okay. Cu, the same element in the periodical table. Copper, the same element found in the periodical table. But it can be made of other materials too. But it can also be made of aluminum, okay? Al. Can be made of silver, huh? Can be made of silver. Okay, which is what's the symbol of silver? Argentine, right? AR. Argentium. The name of Argentina comes from the country Argentina, right? Comes from the symbol, comes from the name of silver in Latin. Okay? Let's take a look here, internet. Here you go. Many of the colonies of Spain were very rich in silver, especially in Bolivia. They have a whole mountain of silver when the Spanish discovered that, and they became very, very wealthy because of it, because of the riches of the America. It's a whole mountain in Bolivia that was made just of pure silver. It's amazing how much wealth the continent had at that time. And symbol, right, for silver on periodic table. Go silver. Oh, it's AG, not AR. It's AG. Argentum. Okay. Have you ever thought why Argentina is called Argentina? It comes from the word Argentum. It's AG. Let's correct that. AG. If you are following the market nowadays, we are getting into big trouble because of silver. Okay. We are running out of silver. If you're familiar with electricity, you'd know that most electrical wire is made mainly of copper, right? Mainly of copper. The same element found in periodic tables. But it can also be made of aluminum, can be made of gold. Gold is Au, aurum, right? Can be made of silver, Ag, and other metals found in the periodic table. Okay. And let's talk about gold, right? Let's talk about gold here. Gold, okay. Why is gold called Au, right? Is derived from the Latin word aurum. In Portuguese, it's called ouro. Almost the same, right? Almost. In Spanish, it's oro, right? It's oro. But in English, it's very different, right? Let's gold. Gold in English, right? Aurum in Latin. Ouro in Portuguese. And oro, right? In Spanish. Who knows Spanish? I think it's without the U, let's say. Ouro, translation to Spanish. Or even better, let's put it gold, right? Gold translation to Spanish is better. Ouro, yeah, very similar to Portuguese. And Spanish and Portuguese is very close to the original word in Latin. Latin. Ah, must. So those are important electrical conductor materials. Copper is mainly used in wiring for two reasons, for two main reasons. One, it is one of the best. I'm not saying one of the best conductor. It is the second best electrical conductor known in nature. And it is also very abundant, cheap, right? Very cheap, very abundant. Can you remember that? Okay. The most conducting the metal that is the most conducting. Want anybody know what's the most conducting metal that we have out there? Anybody knows that? Think about that. If you know, just put that in the chat. The metal that's the most conducting one is silver. Okay, silver conduct better than copper, but the difference in conduction is very small. It's not like a big deal. Okay, the difference in conducting properties of silver is only is better than copper, but is only 6% more conductive. And hell of expensive, right? At this point in time, if you're following the market, something very interesting is happening nowadays in the market, in the commodities market. Go fast, huh? If you're following the commodities market, the price of silver exploded lately. In the past year, the price of silver increased by 130%. Okay, it was I remember at the time which was only $25 the ounce, the troy ounce. Now, depending on the country that you go, especially in China, you're gonna pay $130 per ounce. Just recently, it was just $25. Okay. So we are having a very interesting situation nowadays. The price of silver had kept very stable during several years. I would say even decades. The price of the market in the past was being manipulated to be kept a very low price, just being manipulated by many of the banks out there. But now they can no longer keep on manipulating the market, and because of that, the price of silver exploded. Okay, let's take a look at the price of silver right now, and then we look at the price of copper as well. Price of silver and copper, and don't forget the price of gold also is increasing. What's that? Try new, yeah. Okay, let's see here. Okay, silver approximately. They say $78, but this is not true, okay? Because there's still a premium that you have to pay if you want to pay to buy silver. It's more like that's the paper price of silver here in the United States, okay? But the physical price, if you want to buy actual physical silver, you have to buy more than $100. You have to pay more than $100 per troy ounce. Look at the price of copper. It's not the 575 per ounce. It's 575 per pound. So it's much cheaper than the price of silver, right? And let's see, chart historical data. Let's see if we can look at the historical data here of the chart of silver. So you can appreciate what has been happening to the price of silver lately. Here you go, that for the past year, 5 years, 10 years. No, that's copper. That's not silver. Sorry, that's copper. Yeah, see here, it's copper. Let's see if we have silver here. That's why I thought it didn't make any sense, But the price of copper is overall increasing, right? Over the past 10 years. Let's see, 25 years. Commodities price. Oh, what's that? Okay, available for subscriber. I'm not a subscriber. Let's see if we have the graph, the chart for silver here. Nope. I gotta go elsewhere. So copper increased from $2 in 2017, and now it's being priced at about $6, $5.79. And is this what? Must be the pound, per pound, okay? 1 pound is like 500 grams, right? 1 ounce, 1 troy ounce is 31 grams. So 1 pound is roughly 15 times more than an ounce. So you have to divide this price by 15 to compare the price of copper to the price of silver. So roughly, we are talking about maybe 40 cents per ounce, whereas silver is 75, at least $75. So now you understand why we use copper in our wiring, right? I want to show you the graph of how the silver price is increasing. It's just ridiculous, If you were to invest, if you were to invest in silver in the past 10 years, you had been at least doubled your money. Price, oops, let's see here. Let's go back. Price of silver. Gold and silver price charts. Let's take a look here. Precious metal exchange. Gold and silver price charts. Let's see. Let's see if this one is a good one. JM Bullion. Okay, here you go. They have all the gold, silver, platinum, palladium. They are all metals. They're all good conduct. Bitcoin is not, right? Forget about Bitcoin. Bitcoin is something else. Price charts. Let's take a look. I want to show you silver. Let's see if we can get a good. And don't forget, this price is what we call the spot price of silver in the American market. Okay. Here, the price here in the States, the price of silver is depressed. It has been manipulated for several decades, I would say. But if you really want to buy it, if you want to buy, even in the United States, even here in the United States, if you want to buy silver, actual physical silver, you're not going to pay $78. Okay. Let's take a look. That's one day only. Okay, so today silver price went up 6%. Not bad, huh? 6%, not bad. What about in a week? Okay, see the price of silver is going down for a week, and again that's because the market is being manipulated. Okay, you can see this around $80, $70. The past months, take a look. Price of silver reached more than $100 just recently. But because of market manipulation, people managed to bring it down to $70. There in China, like I said, and not just in China, but anywhere, if you want to buy physical silver, you're going to buy for at least $100. 3 months. You go, look at how the price of silver went up. In 3 months only, 53% in 3 months. Is a superb investment. In 3 months, okay, 6 months. 6 months, 104%. Where are you gonna get this much, this much percentage valuation in your investment? Okay, in 1 year, 1 year is gonna be around 130. Yeah, But it's more than 130 compared to the peak, right? Compared to the peak, it's going to be more than that. But he's referring to today's price. And note, see that it's going almost parabolic right in here, right? And then it crashed. It crashed like something like 30%. Okay. Oh, you can see the market has kept the price of silver low, and even during this period as well, right? And look how it behaves parabolically. Let's take a look at copper. Here you go. That's one day copper went up. And just look, kind of behaving like silver, right? Reached the peak and then went down. Okay. Moved sideways, 3 months, went up, went down. Here you go. It's kind of going almost the same profile as silver all. Okay. And you can look at gold. Gold also has been a very good investment. Lately, right? Lately, it's not always. Those metals, those precious metals, they don't always behave this way. $5,000 the ounce, the troy ounce of gold, compared to what, less than $100 for silver, right? So see, all those metals are kind of behaving almost the same way. They reach the peak, and then people want to take profit. They start buying, they start selling it, and the price goes down. But the tendency is to keep on going up. All those metals, the tendency of all those metals 1 year. Why am I showing that? I'm showing that so you can compare the price of existing metals in the market, of existing conductors in the market. And copper is much cheaper than silver, right? And 579 again, don't forget this price is per pound, it's not per ounce. It's not per ounce troy. Per ounce troy should be around 40 cents, more or less. And let's take a look at the physics of those metals, right? I want you also to understand their conductive properties. There is a way to quantify how well conductive those metals are. How good of a conductors they are. They are. Conductivity of metals. This is actual physics. Okay. High electrical and thermal metals possess high electrical and thermal conductivity, right? Due to a positive or to a lattice of positively charged ions surrounded by a sea of the localized free moving electrons. That's why metals are very good conductive. They're thermal conductor and very good electrical conductor. Because of those electrons, those free electrons that belong to the outer orbitals of the atom, those are called the free valence electrons. Okay, best conductor. Silver is the best one, is the most conductive, followed by copper, gold, but nobody's gonna buy gold, right, to do their wiring, and aluminum. And I want you to see the actual conductivity. Let's take a look here. Resistivity and conductivity, right in here, Wikipedia. Let's see here. The higher the conductivity, the more freely the electrons move. We want a table. Let's see, what is the table here? The table, here you go. Here's the table. Resistivity, we're going to cover resistivity, but we are going to concentrate on conductivity. The conductivity depends on the temperature, okay? And the unit of conductivity is the Siemens per meter. And look at silver, is 63 times 10 to the 6 Siemens per meter. Let's take a look at the Siemens is, right? Unit Siemens. Unit Siemens. So you understand where this unit comes from? Siemens unit. Very important. Okay, that's how Siemens is made up. Okay, kilogram, meter, second, and here amperes is coulomb per second. Let me write that down for you. Okay, so you're not lost in this new notation. You go. At this point in time, let's see here. Silver is costing around $100 per ounce troy, and gold is costing around $5,000 per ounce troy, whereas copper, we saw what, 574, right? 570. Oops, per pound, $5.70 per pound. And we can start to come up with a table. You go. Let's see. Gold, copper, silver, copper, gold, and aluminum. I'm going to put only 4 metals here, okay? And we are talking about what price? We are talking about electrical conductivity. Let's put metal conductivity as well, so you can compare them all. And I think I'm going to need another one. Another right here. Here you go. Metal. Argentium. Silver. Copper. The next one is aurum. Gold. Next one is aluminum. And what we're going to do here, we're going to do US dollar sign per ounce. So let's put per ounce, and we change it electrical conductivity. Electrical conductivity. The symbol for electrical conductivity is this sigma. What is the most conducting is silver? Silver conducts better now. Let's see here. Let's see. Let's put that electrical conductivity. I don't. Electrical conductivity. The symbol for electric conductivity is this sigma letter. Okay, and the unit for sigma is Siemens per. Let's take a look here. This one right here. Siemens per meter. The Siemens per meter. And Siemens, S equal to Siemens, is made up of the following units, SI units. Okay, you go. Going back to our second cube. Wow, let's put it here aside. We're gonna write it down. Let's see here. I wanted to insert this guy equation. Another a student coming in. So S equal to Siemens. Let me erase that. Right, Siemens is second to the cube I'm just copying what I see here in Wikipedia. Kilogram, meter square. Okay, and we also have ampere, ampere to the square. Let me tell you what ampere is. We didn't cover the unit ampere yet, but we have already covered the other units, right? The unit of ampere is what? Is coulomb, the unit for charge, divided by second. Okay? And let's see what else it gets us. Or else it gets us. Coulomb becomes squared. Second becomes squared. And second square cancel to second cube, so we will end up just with a single second there, right? And that's what Siemens is all about. And the unit of conductivity, okay? The unit of conductivity becomes right? Siemens per meter, right? We don't need that anymore. All we need to do is to adjust this other one. It becomes second coulomb square kilogram cubic meters. Okay? That's what the unit of conductivity is all about. It depends on the mass of the metal, of the conductor. Depends on time, depends on the length of the conductor as well, and how many coulombs it can carry, right? That's, and let's see here. I'm gonna put it, why did I do that? Because I didn't want to write down all that stuff. All I want to do was to simplify what we have here. Thermal conductor. We'll worry about thermal conductor soon. Metal. Here you go. Per ounce, I'm gonna put it approximately $100. Copper. We have to translate dollars per pound in dollars per ounce, right? Copper, let's see, that's the one. No, that's not the one. It should be this one here. Which one was I using? This one, right? Yeah. I was using this one here. Yeah. Oh, we can change. No, we cannot change. Too bad. US dollar. Silver, can we change to pound? I don't think so. Just try ounces. Yeah, you can't. Okay, so we have to translate copper from pound to ounce. 1 pound is approximately 500 grams. Not exactly, right? It's a little bit more than that. Maybe 550 divided by 31 grams. That's 1 troy ounce. So we are talking about 17 times. So this number that you see right now must be divided, this value that you have right now must be divided by 17.7. So here you go. Minus 1 times 578. 32 cents, 33 cents. Okay? Approximately 33 cents. $0.33. Gold, I know, is around 5,000. The price oscillates, okay, but and don't forget, if you can find an ounce of silver for $78, buy it. Don't let it go, okay? Nobody's gonna sell you silver for that for $70, $78. They're gonna sell you by at least 110 or 120, even in the States, even. Aluminum. Let's take a look at the price of aluminum. I didn't have aluminum here. What a shame. Ah, okay. Okay, they don't have. Let's take a look. We have others here. Let's play with platinum, right? Platinum is a very good conductor as well. Platinum is far more noble than gold, but its price is lower. See that? It depends on the timeline. Platinum should be supposedly was supposed to have a higher price than gold. 2098. That's ounce Troy. 2098. Platinum PT, right? 2098. Another one. Let's see which one can we get it. Palladium. Palladium has very good industrial applications. 1,747. That's today's price, okay? This price can change. PD, right? 1,747. These prices keep on oscillating depending on the demand. And let's take a look at the thermal conductivity. I don't think I need this one. I'll keep it anyway for now. Electrical conductivity. Electrical conductivity. Silver, 63 times 10 to the 6. 63 times 10 to the 6. Copper, 59.6 times 10 to the 6. They are all multiplied by times 10 to the 6, okay? Here you go, times 10 to the 6. Let me copy everything here. And then I just put the aurum or gold, 41.1. Aluminum, 37.7, not bad, right? Almost half of that of silver. A little bit more than half, sorry. A little bit more than half that of silver. I put platinum, let's see, platinum. Platinum, 9.43. 9.43 times 10 to the 6. What about palladium? Let's take a look at palladium. They don't have palladium here. Or have, do they? Let's see. No, they don't have. What a shame. They don't have palladium here in this table for some reason. Okay. I'm going to put a question mark right in here. And let's make sure. Here you go. Wikipedia. That's the table I'm talking about, right? There are many other metals out there. Copper, added copper, gold, aluminum, brass, calcium, rhodium, tungsten, zinc, brass, cobalt, and so on. Nickel, ruthenium, all those are metals. Platinum right in here. PT, symbol of platinum. For some reason, they didn't put palladium there. I do not know why. But they do have the electrical resistivity here of palladium. We have to change the unit. Electrical resistivity. Well, I'm not going to struggle with that, okay? Well, I guess you are getting the idea, right? Aluminum and let's stop right in here. Percentage difference, okay? Percentage difference compared to silver, right? Let's put that 0%, right? And let's see about copper. How much of a percentage difference it is between those metals with respect to silver. With respect to silver, 59.6 is roughly 6% from what I recall. Okay, divided by 63. Yeah, 5.3%, 5.4%. 5 less conductive than silver, copper. And yet the price is 100 times more, right? More than 100 times. 200 times more? No, 300 times more. The price of copper, the price of silver with respect to copper. Percentage difference in thermal conductivity, right? Here, 41. 41 divided by 63 minus 1. 34% less conductive, 35% less conductive. Aluminum, okay, 37, 1, 2, 3, 37.7, 40% less conductive. Platinum, 9.43, 85% less conductive. Okay, that's what we have. And in terms of price, we can also play with the price as well. To the left, in terms of price, right? Sigma. Percentage difference in US dollars. So difference in USD. Okay. Here is 0.33 divided by 100. Here is 0%, right? Copper is, my goodness, 3,000 times, 0.0033 cheap, the price of silver. And now gold, oh, and by the way, gold per silver right now is 50, right? And that's a very important ratio, gold to silver. Right now it's around 50. Let's take a look at the table here. This table that we're looking at had the gold to silver ratio as well. Yeah, see that gold to silver ratio right in here is a very important ratio. How expensive gold is with respect to silver. Right now is hovering around 64. 64 times more expensive gold is, but historically speaking, gold has been 17 times more expensive, historically speaking. So we believe that silver is undervalued at this point in time. We believe, because historically speaking, gold was supposed to be only 17 times more expensive than silver. Okay, it went all the way up to almost 100. Let's take a look here. Yeah, see that? Almost 100, 1 year. So many people think that silver is still very cheap because of this ratio. The historical ratio of gold per silver is around 17, which is also the abundance of gold with respect to silver. In the crust, in the Earth's crust, there is 17 more silver in the Earth's core crust than gold. So because of this ratio is much greater than 17, right? We believe that silver is underpriced. Either silver is underpriced or gold is overpriced. It went all the way down to 32 back in 2011. Okay, so we are talking about again around 64 at this point in time. Gold and silver ratio is 64. Aluminum, I don't have the pricing, right? And then we can, this one is going to be 21 platinum. This one is going to be around 70. Okay, those are rough numbers. Like I said, I put $100 here because that's what the real world is charging you, not the paper world. And this ratio that you saw right in here accounts for that undervalued price of silver, right? So this ratio should be a little bit less than that in the real world. And remember the conductivity. Copper is just 6% less conductive than silver, and yet its price is 100 times, 300 times less. 300 times less than the price of an ounce of copper. That's why we use copper. But there are many applications out there that require silver no matter what. Okay? That's why people say the price of silver should go higher and higher. I'm betting on that because I put my money on that. Here you go. Let me bold face it. Bold face it. Let's see. Any questions about that? Okay. Keep that in mind. I didn't put the thermal conductivity here of silver because I don't want to spend more time on that. It is, what time is that right now? Yeah, it's time for a little break, right? But before the break, let me take attendance. And I didn't cover the electric field. What a shame. I got so involved with this thing. I want to show you that. I ended up not covering electric field. But we can adjust that. Let's see here. Marketing, pending invoice. Here you go, right in here. I need this one as well. I want the roster. P07 roster. Let's take a look at this one. Yeah, I correct that, Chris. Thank you for letting me know. It's silver, not AG. Yes, AG. And again, I want to ask you, who doesn't have a group, right? I already know that Chris and Juan do not have a group. Is there anybody else that does not have a group? Today is the 18th. Let's see. Mikara Alkema, are you there? Let's see. Oh, yeah, Mikara is here. Hello, Mikara, can you hear me? Looks like Mikara is away from the computer. Ryan Alkema, are you there, Ryan? Okay, I'm gonna put a star here. Ryan.
Hi,
Yeah, who is that?
it's Oni. I was just saying that I'm here. I wanted to tell you that I'm here because I heard that you're taking attendance because I have to go do something real quick. So
Okay. Okay,
I'll
so Oni, right? Your group number one, right, Oni?
yeah,
Yeah. Okay.
I'll be right back. I just have to go do something.
Okay. So
So
someone else is trying to come in, Kimberly. Let me erase that stuff here. I take attendance the first 2 weeks because we have to keep track who's coming the first 2 weeks, right? And Luis Diego Cruz, are you there, Luis?
I'm here.
Yeah, you do not have a group, right, Luis?
I don't know.
Do you know? Yeah, no, you do not have a group for sure. I can tell you
Yeah,
for.
no.
Do you know anybody in the class that you'd like to team up with?
No, no one.
Okay, so let me check who doesn't have a group, and then I will team him or her up with you. Okay?
Okay, perfect.
Jenny, are you there, Jenny? Jenny Maldonado. I see Jenny here.
I'm here.
Okay, Jane, you would like to team up with Luis Diego?
Yeah, that
Okay.
works. Thank you.
Exchange your phone numbers and contact information, right? So you're gonna be group number 16. Group number 16. I have to do some other things for you. Okay, so hang in there. Mario Showa, are you there, Mario? I don't see Mario. Nope. Next is Ahmad Olumi. Ahmad. Yeah, I don't see Ahmad. Next is Tatiana Saldivar. Tatiana, I don't see Tatiana either. Next is Francesca Sorrentino. I don't, oh, I'm here. Okay, thank you. Mikara, and I see that Ryan has the same last name as you do, right? Yes, okay. Are you brothers and sisters? Siblings, yeah, siblings. Okay, so why don't you join the same group? Here, we're going to be group 17, you two, okay? And 1 and 1, right? Yeah. Okay, so 17. Francesca is not here, right? Next, Chris. Chris, so I teamed you up with 1, right, Chris?
Yes.
And so you're going to be group number 18. 18, Juan, are you still there? Okay, good. Good. So, Delacia. Let's see, Delacia is in the same group as Ani, all right? Yeah, okay, that's okay. Mirage, are you there? Mirage Abassi. No, doesn't look like. Susan Acosta. Susan Acosta. Okay, Susan is here. Right, Susan? Just send me a text message. I'm going to put a star here under your name. Looks like Susan's away from her computer. Evelyn Ayala. Okay,
I'm
good.
here.
Thank you. Thank you, Susan. What about Evelyn?
Here.
Okay, good. Cristina Balderas. Let's see if Christina is here. No, I don't see Christina. Next, Queen Castaneda.
Here.
Thank you, Queen. You already have a group member, right? So Emily Serna.
Here.
Thank you, Emily. Isabella Cisnero. Isabella, I don't see Isabella here. Gabriela Edwards.
Here.
Okay, thank you, Gabriela. Princess Gate.
Here.
Thank you, Princess. Kimberly Morales.
Here.
Thank you. Next, Trin Hernandez. Let's see if Trin's here.
I'm here.
Okay. Okay, iPhone, right?
Yeah.
Okay, thank you, Trin. Stefan.
I'm here.
Okay,
I'm here.
thank you, Stefan. Jeremy Landis. Don't see Jeremy here. Yeah. Paola Leones. No. Let's see, Jeremy is not here, right? So Paola is not here either. Let's go all the way down. Here we go. Pedro Lopez.
Here, Professor.
Thank you, Pedro. Isabel Medina. I don't see Isabel. Arian Navides.
Yeah,
Hello, Arian.
Professor.
Okay.
Hi.
Thank you. Okay, thank you. Arwa, Paris. I don't see Arwa. Okay. Catherine Perez. I don't see Catherine either. Nadia.
Here.
Thank you, Nadia. Jason Cervellon.
Here.
Thank you, Jason. Dana Terry. Okay, thank you. Ramon Moran. Ramon.
Here.
Thank you, Ramon. Audrey.
Here.
Thank you. Next is Carlo Gallardo.
Here.
Thank you, Carlo. Steve Sanchez.
Here.
Thank you. Ben Bandoya. Okay, thank you, Ben. And Noemi Martinez. I don't see Noemi. Okay, is there anybody else that was not called? And anybody else that does not have a group? Okay, so let's see how many students I have here. 26, 25. Let's see here. 26. So there's one student that was everybody called, by the way? I'm getting one more student here that attended, is attending, but didn't get a attendance. Okay, well, we'll figure that out later. Okay, so it is 10:50. 10:50 right now. We are gonna have our break. Break 10:50 a.m. to 11:05 a.m. Okay? And I see you in 15 minutes. See you soon. Stop sharing. I am back here. Let's see. We had everybody again. I'm gonna ask again. Everybody has a group. Everybody has a group.
Yes.
Okay. Anybody doesn't? Let's see. I'm seeing here. Yeah, Paula does not have a group, right? Oh, no, Paula Leonis has. Okay. It's the other Paula that doesn't have a group. Okay. Paula Leonis, are you there? Yes, okay, good. Thank you. Your group number 8. And what I have to do now, again, if you don't have a group, let me know. And I have to prepare the group folder of those 3 groups here, right? Let's start with group 16. One more student. Okay, Jeremy now is coming. Good. Physics 7. Good. Let's let's see how I'm gonna do that. new folder, group number 16, group number 17. Okay, thank you, Jeremy. And group 17, let me get that here. One more. Thank you for letting me know, Jeremy. Group number 18. And now, group 18 here. Okay, good. So let me move aside here. Share. Okay, restricted. Anyone use the link? Viewer, editor, copy link. Okay, now group 16, Luis Diego Cruz. I'm going to, Luis, I am sending the link to your group folder, your lab group folder in the chat box, okay? And keep this link for the rest of the semester. You'll be using this link. And the other student that's also in group 16 is Janie. Janie Maldonado. Okay, here's the link to your group folder, Janie. Don't share this link with anyone else, with anyone outside your group, okay? Only you, Janie, and Luis have the same link. Okay, now let's go for group 17. Share. Restricted. Anyone with the link. Viewer, editor. Copy link. Done. 17 is going to be Mikara and Ryan. Mikara, you have your link for your group folder. And Ryan, let's get Ryan here as well. Here you go, the link for your group folder in. Okay, so keep this link in a safe place, somewhere that you can access it easily. Someone is trying to come in, right? No? Okay. No. Okay, one more, right? Chris and Juan. Share. Restricted. Anyone with the link. Viewer, editor. And I'm going to copy this link and send. Here is your link, Chris. Keep it in a safe place. And Juan as well. Only you, Juan, and Chris has the link. Don't share that with anybody else. Unless I tell you otherwise, okay? Let's see, someone is, thank you, okay. Make sure this link worked well, okay? For all those groups who got the link right now, 16, 17, and 18, make sure once you click in your link, make sure you are in your group folder, right? Like for instance, if you're group 16, you're supposed to land right in here in this page, right? With group 16 here at the top. If you are group 17, once you click the link, you are supposed to land right in here in this folder, group 17, and so on, right? and so on. If you don't see what I am seeing here, let me know, and we'll troubleshoot. We'll figure out what's going on, okay? 26. Okay, good. Any questions before we proceed? What I want to do right now, let me cover the theory behind this lab, okay? Let me cover which relates as well to the, which also related to the material, to the lecture material. And okay, now you know that there is electrical conductors, right? And there are also electrical insulators. Here you go, electrical conductors here, electrical insulators here, okay? And the main difference is that the electrical conductors allow electric charges to move freely. And here I have an illustration for an electrical conductor. Suppose that I somehow manage to put a bunch of electric charges in a single place here, in a single region of this electrical conductor. What's going to happen, right? As time goes by, that's T equal to 0. T equal to 0, okay? What's going to happen to those electric charge? I want you to imagine, because this material allows the charge to move freely, okay? Initially, what you're going to have, each of those charges are going to exert an electrical force on them, okay? On each other, okay? So here you go, this charge here is going to repel this one. This other charge here is also going to repel this one, and so on, right? And eventually, this charge here at the extreme left will move, you know, let's say here, will move away from the others because of the electrostatic force that you are having here. Because those charges can move freely in this conducting material, eventually there will be a point of equilibrium in which all the charges are going to be positioned at the edge of this conductor. Okay, there still will be an electric force on them. Okay, there is still, for instance, this charge right in here will feel an electric force from the other one that's going to be in this direction, right? But this charge also is going to feel another electric force that's going to point in this direction here. Do you see that? And so on, right? This charge is also going to apply a force and so on. But because this charge is very close to the edge of this conductor, the edge of the conductor, we're also going to apply a mechanical force, not an electrical force, but a mechanical force that's going to cancel out all the other electrical forces that are acting here in this electric charge. And the charge is going to remain here at this position. The same thing applies to the other charge. Makes sense? This is just a qualitative treatment because there's no other better way of treating this at this level, okay? So in a conductor, if there is no other electric force acting on those electric charges, all those electric charges are going to tend to move towards the edge of the conductor. It doesn't matter if you put them here at this spot or if you put them here at the very center. They will all end up at the edge of the conductor. They won't be able to jump out of the conductor. And that I put here, long time. Okay, that's how electric charges behave inside electrical conductors. Okay, that's not what happens with electrical insulators. And it's exactly because of this behavior that we can use electrical conductors in our wiring, okay? But it's not the same thing that happens with insulators. If we concentrate an amount of charge at a given spot, after a very long time, the charges are not going to move. They're going to remain in the same spot. Okay, and what are good electrical insulators? Plastic, glass, wood, etc. Okay, so there is metals are very good conductors, and those other materials are very good insulators, electrical insulators. Let's see here. Good electrical conductors, right? I'm gonna good electrical conductors. Metals in general, right? Silver, copper, gold, etc. Good electrical insulators. Wood, plastic, glass, etc. Paper, can put paper here. Paper. Deionized water. That's why it's called deionized, because it has no ions there. If the water had an ion, it should be a conductor, etc. Okay? Now, the core of a wire, of an electrical wiring, an electrical wire is made of a metal, which is your copper metal, for instance, copper wire. I think copper wire. But it is important to insulate this wire. For that, we use plastic around it, right? To insulate. Otherwise, you may have a short circuit. Okay, so wires that we have there at home is made of both insulators and conductors. The core is a conductor, the good conductor. The sheet around it, the core, is made of an insulator, so you do not have problems with the charge. Okay, that's what I have. Okay, let's take a look at the other concept. Okay, the concept of electric field, which is the material for our first lab. Remember what we said about electric forces, right? Suppose that we have an electric charge here in space, and charge Q1 is a positive charge, and I'm going to come up with my frame of reference, my axis of reference. In physics, we also always put an axis of reference, a frame of reference, x-axis, y-axis. And what else I'm going to do? I'm going to put another electric charge nearby this other one, okay? And this electric charge, I'm going to call lowercase q, subscript t. T stands for test. It's also a test charge, okay? Test charge. And this test charge has a very important characteristic. Is a charge that has a charge value that's much less than the charge value of this other main charge, okay? We need to define that in this way to define the electric field. And the test charge must always be positive, okay? So let's go back to our notes here. Electric field. Electric field. To define the electric field of a main charge Q1, okay? Comma, we need to consider a test charge QT. We need to consider a positive test charge, QT, whose value is much less than the main charge Q1. Okay, that's how those are the conditions that we need to define the electric field, and there is a reason for that. Okay, I'm gonna tell you exactly why it's like that. Okay, what else? Okay, and then when we put this charge, test charge next to the main charge, what's going to happen? You know that there will be an electrostatic force interaction between them. Okay, this main charge is going to exert an electric force on the test charge. Up to now, there's nothing new here, right? Force of charge 1 applied to the test charge is a repulsive charge in this specific case. Okay? Now here we go. We have this vector position that goes from the charge number 1 to the test charge QT. Here you go. That's the vector position. Let me get this guy right here and paste right here. Right? Now, if we eliminate this test charge from that very spot that you see, what's going to happen? The force, the electric force is going to disappear. The electric force is going to be 0. Do you agree with that? But we do know that something else is left behind. And this something else is the electric field. Okay? And that's how we obtain the direction of the electric field, by considering a test charge, a positive test charge in that spot in the space. Okay? If we want to, and there is a very important correlation between the electric field with the gravitational field. We can do exactly the same thing to find out not the gravitational field, but the acceleration of gravity. I mentioned that to you before, right? In the previous meeting. Okay. The electric field, recall that the electric field is the electric counterpart of the gravitational acceleration or gravitational field. There's another name for the gravitational acceleration, okay? You can also call it the gravitational field. Okay? And we can apply the same explanation for the gravitational field. Let's see if I have a slide that explains that. I don't. Oh yeah, I do have. Okay, here you go. Here's the case of the gravitational field, right? Nearby the surface of the Earth, if we put a mass nearby the surface of the Earth, I'm gonna, you know what? Let me see. This is something else. Let me see if I can illustrate it in a better way. Let's see. Yeah, I'm gonna do it in the following way. The analogy is for the gravitational field, right? And I'm going to do exactly what I did here for the electric charge. Okay, so here you go. I move that same test charge elsewhere. I have that repulsive force, and this repulsive force tells me that what's the direction of the electric field at that other spot, and so on. What I'm doing here, I'm mapping the electric field around this main charge Q1. That's what I'm doing, okay? Closer to the charge Q1, the electric field is going to be a little bit more intense, which is the electric field 4, and so on. And I can do the same thing for the mass. Oh, here you go. I can do the same thing for 2 masses. Here you go. Here's the mass of the Earth, M1. x-axis, y-axis, right? I go get a very small mass, my test mass, can be an apple, Newton's apple, can be a small satellite. I put a very large here, okay? According to the law of universal gravitation, this test mass will feel an attractive force towards the main mass. And I'm going to do the following. I'm going, instead of putting big M, I'm going to put small m, just to be consistent with the notation that I used before, right? Here you go. The gravitational force. Okay, any questions so far? Okay. Now, if I remove this test mass, just like before, the force is going to be 0. But something else is going to be left behind. And this something else is the acceleration of gravity, or the gravitational field. Okay. Someone ask a question here? Kimberly, do you need to ask a question? Okay, so I'm going to mute you. Okay, Kimberly, here you go. And then if you want to map the gravitational field, you do exactly the same thing that we did for the electric field, right? Put this mass, test mass elsewhere. Let's see, vectorial representation of the issue. Elsewhere, and you're going to get, let's repeat, right, exactly what you did. I'm going to use this slide right here. Instead of Q, I'm going to put M, right? And I don't need the positive sign anymore. Mass 1 of the G field. I'm going to put a G field now. And instead of being away, it's going to be towards. All I have to do is to, no, that's not what I want. I want something else. Format. All I have to do is to change the direction of my field. Yeah. And this one here. Okay. And I'm not going to name it E1. I'm going to name it G1. Make sense? Okay. Here I do the same thing. I invert the direction of this field, right? And exchange the notation by G2, right? And so on. Did you get the idea? That's a very good way of understanding a very abstract concept like the electric field. Okay? That's the gravitational, and the position of the gravitational field is exactly where the end of the arrow is, okay? At this spot, the gravitational field is towards the mass. The length of the vector tells you the value, the numerical value of the gravitational field, right? And the direction of the arrow tells the direction of the gravitational field. It's pointing towards the center of mass M1. Okay, that's the idea of the electric field. Okay, how I'm going to put that down? The electric field can be defined as the ability of a given electric charge to exert a force in a given point in space, just like the gravitational field, right? The gravitational field, here you go. The gravitational field, we didn't define that in physics 6, but that's how you can define it. Can be defined as the ability of a given mass to exert a force And I'm gonna put it a gravitational force, okay? And I'm gonna put an electric force at a, not in, right, but at a given point in space. Electric field versus gravitational field. And that's what the first lab is all about. It's about mapping. The first lab is about mapping the electric field of a given electric charge distribution. Okay? Okay. So what you have seen so far, so far, we have illustrated only the E field of a point charge. However, you can have also the electric field of an arrangement of multiple charges. You can also obtain the electric field of an arrangement of multiple charges just by using the superposition principle. Because the electric field is a vector, then the superposition principle also applies to the electric field. Let's see if I have a nice... Here I did just for a single point mass and a single point charge, but you can also have for multiple point charge. Let's see if I have it here. Yeah, I do have it. Here's an example of the electric field of the electric field due to more than one point charge. Okay, the electric field of 2 positive point charges. And you can obtain that in a very easy way, in a very simple way, just by doing those simple drawings. You're not gonna get the exact mathematical formula for that field, but you're going to have a very nice qualitative idea of the feature of this electric field, right? So we start with a x-axis, we implement the y-axis here, and then, I'm gonna put one charge here to the left of the origin, and another charge on the other side. Both charges are positive. They are equidistant from the origin of the axis. If I want to know the electric field at this spot here along the y-axis, all I have to do is to play that little game that I taught you already how to do, right? Consider the electric field of the charge at the left and the electric field of the charge at the right. The electric field at this point is going to be given by the superposition principle, which is nothing more, nothing less than the vectorial summation of those two fields. Because those two charges have the same magnitude and they are equidistant to this point here along the y-axis, the magnitude of this field is going to be equal to the magnitude of this other field, right? It's just the direction that's going to be different. And here you go. When you sum those two fields, we get an electric field in this direction. Okay? Here you go. And there is more. If I want to find out the electric field elsewhere, the electric field here along the y-axis is easy, right? Because we're dealing with electric charge, because we're dealing with distances that are the same. But if we try to map the electric field elsewhere, outside the y-axis, it's going to be a little bit more difficult. And that's what we are going to do that now. okay? At this very point, just at the top right of my left charge, the electric field definitely is going to be in the vertical direction, right? But then the contribution of the other charge is going to be a little bit to the left. At this point in space, the electric field is going to be given by this net vector, okay? And here you go, I'm mapping the electric field in space. That's the qualitative idea behind the electric field and the superposition principle. Here you go. And I can do that for this other position, right? To the left, along the x-axis. Along the x-axis is going to be easy, because the electric field of the left charge is going to be pointing in the negative x direction. But the electric field of the other charge is going to be pointing to the left direction as well. That's what you have right here. Let me just do it step by step, so you don't get confused. Here you go. At this point here along the x-axis, the electric field is going to be to the left. And now I'm going to come up with another one. And now what about the electric field of the charge at the right side? It's still going to be pointed along the negative direction of the x-axis, but its magnitude is going to be a little bit smaller, okay? And that's what is illustrated in the next slide. I had to shift the electric field of the other charge so you could see it more easily, right? Let's take a look again. Here you go. Electric field due to the left charge, electric field due to the right charge. Okay? When you come up with the superposition of those two fields, you get an electric field that's a little bit longer. Do you see how you can map the electric field in space? What about at the origin? At the origin, those two electric fields are going to cancel each other, okay? So the net field at the origin is going to be 0 for this specific electric charge distribution, okay? What I didn't tell you is the mathematical formulation of the electric field of a point charge. It's not difficult, okay? The electric field of a point charge can also be written in terms of the Coulomb's law. Coulomb's law, okay? It's mathematical. Okay, so going back to the Coulomb's law, we have what we have to do. We have to get the force between my main charge, okay? Force between my main charge 1 and my test charge T, right? Remember that? And that's gonna be what? K Q1 Q test divided by R squared, right? And we still have that unit vector, okay? Unit vector, I'm gonna call unit vector position of the test charge with respect to the charge 1. So is going to be the unit vector that goes from charge 1 to charge T. Okay. Oh, and by the way, it's a unit vector. It's not a regular vector, right? Let me put a hat. Yeah. Oh, I gotta do something else. Yeah. Let's see if I can fix that. Yeah, I can fix that. Here you go. That's the mathematical formulation of Coulomb's law in vectorial format. Vector position going from charge 1 to the test charge, okay? The electric field, the definition, the mathematical definition of the electric field is, okay? Of the electric, and when I say that the electric field of charge 1 is what? We're going to use this notation here. It's going to be the force that charge 1 applies at the position of the test charge divided by the test charge itself. That's how we define the electric field, okay? And then E, okay? Yeah, that's vec. So that's the end. I'm going to put as well, oops. Here you go. See? That's the electric field of charge 1. Okay, and now I can drop this T from the formula, okay, because I don't need that anymore. There's no test charge here on the right side. That's the mathematical equation for the electric field of a point charge. This is the mathematical equation of the electric field of a point charge. Okay. The mathematical equation of the electric field of 2-point charges is also obtained using the superposition principle. Superposition principle. I showed how to do that in a qualitative way, right? And now I'm going to show how to do that in a mathematical way. Okay, so here we go. 2-point charge is going to be, here you go, the net electric field, right, at a given position. I'm going to put like that. Here you go. Net electric field, right, is going to be electric field of, electric field of charge 1 plus electric field of charge 2. And how do we write? Okay, we write exactly like we wrote. Here you go. KQ1. Q1 stands for charge 1. KQ2. And by the way, it's going to be here. I have now to write down _1. Okay, distance from charge 1, distance from charge 2. And here it's going to be unit vector from charge 2. Okay. So what I did in this case here is exactly what I did there, right? Here you go. See, that's, so let's say this one would be charge 1, this one would be charge 2, right? Electric field of charge 2. That's exactly what I did here. Mathematically, it's a little bit more difficult, right? But it's very useful when you are doing research to express those fields in this way. What time is that? Okay, let's go another. Let's see. We have 27 students. Let's see with you. I have 26 here in my roster. Was everybody, let's see here. Was everybody called? Let's see. Mario Shoa, are you there? No. Ahmad, are you there? No. Tatiana. Let's see if Tatiana is here. No, Tatiana is not here. Francesca. I don't see Francesca. Chris is here, right? Okay, I just want
Yes,
to,
I'm here.
yeah, Delisha is not here. Let's see. Mirage, are you there? No, Mirage is not here. Cristina Balderas. I don't see Cristina Balderas either. Isabella Cisnero. Oh, Gabriela is here, right? Hi, Gabriela, are you there? Okay, I'm gonna put a star in Gabriela's name. Okay. And let's see, Jeremy. Jeremy is here too, right? I saw Jeremy. He was having a problem with his internet. Isabel Medina. I don't see Isabel Medina here. Arwa. Next is Catherine. Nope. Let's see here. Next, Noemi. Are you there, Noemi? No, I don't see Noemi either. Good. So we're gonna go for our break again. 11:48 right now. Break 11:49 a.m. right to 12:04 p.m. Right, 12:04 p.m. Any questions before we go to the break? I'm covering, like I said, I want to cover this material before we get into the lab, so you understand what it really means, okay? So I see, oh, someone asked the question. Let's see here. Steve? Is attendance only mandatory in the first 2 weeks? Yes, that's right, Steve. Make you gotta be in a group, right? I have to put you in a group, because if I don't put you in a group, how are you going to do the lab, right? Okay, so it's already 11:50. 11:50, 12:05, and I see you in 15 minutes. I'm back here. Okay. Let's share the screen. Okay, so that's also what you see here. The electric field of a point charge is also called the Coulomb's law, okay? The above equation is also called the Coulomb's law. And let me just, we are not doing the lab today, okay? We have to do that for the next time. Let's see here. Let's field the lab one. Lab one. Here you go. Wednesday. Lab one. Electric field one. There are two labs. One is the electric field one, the other is electric field two. And in addition to the electric field, we also have to cover the electric potential. Okay, so let's electric field, here you go. Yeah. Let me erase that. Electric field and electric potential. Electric potential. Okay. Let's see. That's gonna be electric field 1. Electric potential. Electric potential 1. Let's see if we can cover that. We are recording, right? So let's do some examples of this electric field, right? Here you go. Consider finding the electric field of this charge configuration along this axis, okay? Example. Find the net electric field of two of the following charge distribution. The electric field along the y-axis, okay? Along the y-axis of the following charge distribution. And the charge distribution we're talking about is this one here that you saw. Let me copy and paste that. Snipping tool. Right in here. You go. Didn't copy apparently. The snipping tool, they changed it, you know. It didn't used to behave like that, the snipping tool. And recently, looks like Microsoft changed it. Well, where is it? Hey, it's not copying. Oh, I hate that. Let's try again. Okay, press. Here you go. Here's the snipping tool, right? It's supposed to copy this thing. Now, here you go. Capture, right? I want to capture. Then what happened? Disappeared. Anybody knows how to fix this problem? The snipping tool didn't used to behave like that before. Anybody knows how to fix this problem with the snipping tool? It didn't. To start a snip, press what? Window, Shift, S. Let's see. Okay. Now let's see if it's gonna work. Okay, let's see if it works, right? Control Enter. Save, capture. Copy only. Let's copy. Okay. Now, screen copy. Okay. Like I said, this snipping tool didn't used to behave this way before. They made some major changes to snipping tool. Okay, so that's what we want. Wait a minute, I don't want to copy this one. I want to copy this one here. Yeah, that one I want to copy. Let's do that again. Snipping. Let's see. Copy only. Now, this one here. Up. Go. Okay. That's the find the electric field along the y of the following charge distribution. Q is greater than 0. Okay, just right. Find a mathematical expression, for the net electric field along of the following charge distribution. That's the charge distribution that I want. And here you go. Solution. Okay, like that. The solution is going to be something like that. There you go. The net field along the y-axis, charge 1 plus charge 2, right? Here is going to be, instead of Q1, is going to be Q. Instead of Q2, it's going to be Q. Okay? The distances are the same. The distances are the same because it's along the y-axis. Right? And the unit vectors, I'll keep them this way for now. Let's see, what else can I do to simplify? Here you go. R1 square is going to be given by A square plus Y square, right? R2 square is going to be given by the same relation because they are equidistant to that point. The only mystery is R1 and R2 here. That's the only mystery that we have to face now, right? We can write R1 hat and R2 hat in terms of X hat and Y hat, right? What do you think? We can write that down in terms of X hat and Y hat. So let's write that down here. It's going to be something like that. We can also take a look here at this drawing, right? You see here? R1 hat has a X component and a Y component. Both the X and Y components are positive. Both, okay? The only difference here is that the X component of this R2 hat is going to be negative. That's the only problem. That's the only difference. I'm going to write that down, R1, like that. Here you go. R1 is going to be A times X hat. I do not know what A is yet. Okay? Plus B along Y hat. Okay? And then we have something similar, but not exactly the same. R2 is going to be, remember I told you the component, X component of R2 is negative. Okay, A and B. Okay, where A is greater than 0, A and B are both greater than 0. Okay, are both greater than 0. Makes sense? Now we're going to find out what A and B are. Okay, we're going to find that out, and we can do that by verifying the drawing that we have right in here. Okay, so let's say A is going to be, let's say this angle here is an angle theta. A divided by 1, right? Why by 1? Divided by 1 because you are talking about the unit vector r hat 1, okay? Unit vector r hat 1 is parallel to the electric field E1, okay? A divided by 1 is cosine of theta. B divided by 1 is sine of theta, makes sense? And I'm calling that the theta angle right in here. A. Okay, so let me copy that. A is cosine of theta. And then very soon I'm going to show you how to calculate the theta. Okay? And B is going to be sine of theta. How do I calculate theta? You can even calculate sine of theta. Going back to the drawing board, right? Theta is this angle here. Okay? But this theta angle is also equal to this theta angle, right? Make sense? Let's see if I can get. Here you go. All right. Home. I want. Let's try this one here. No, let's see. I want to center this guy right in here. Right in here, okay? I'm gonna put this guy a little bit higher. Copy and paste. And then Q is theta. Okay? That's the angle theta. But this one too is the angle theta. This one is also the angle theta, right? A divided by R. A divided by R is equal to theta. Okay? Sine of theta. No, cosine of theta. Oops. Oh man, I came up with the wrong. It's not A. I gotta put something else here. Okay? Let's call it C instead. Because A is already this distance here. Okay? I chose, okay, C is equal to cosine of theta. B is sine of theta. Better. And by the way, equal. A divided by R is cosine of theta as well. A divided by R. And here is going to be Y divided by R. Okay? Now we have C and B in terms of known values. And we can finish writing our stuff down. Okay, here we go. A divided by R. Y divided by R. A divided by R. Y divided by R. There you go. No, yeah. So we are done. Basically, we're done here. Let's see, where is this one? This one right here. I'm gonna take from here. Okay. R1 hat. This one here. R2 hat. Minus. Here you go, like that. And you already know that this electric field doesn't have an X component, right? Do you see here? You already know from the previous analysis, from the qualitative analysis, that the electric field does not have, the net electric field does not have an X component. And indeed, this formula, this mathematical formula, shows right now that the X component of the net field is canceling out. Do you see that? Okay. And let's see, this term is exactly the same as this term. Recall that R is the square root of this term, right? So our problem is almost over. Let me go to the next line. Yeah, here you go. Another student, this coming. Okay, this one cancel out with this one. We are left. That's gonna be, let me arrange it better. Like that. Like that. But the y components, they do not cancel. They do not cancel each other. The y component. Let's see if I can put some of that stuff in evidence. No. Okay, it's gonna make it simple, very simple, right? This term here is exactly the same as this term. So it's gonna be twice, right? The only other simplification that we can do is he write this R in terms of A and Y. I'm gonna do that right now, downstairs here. Nope, what happened? I copied the wrong one. This one here. Here you go. Put the square root right here. Here you go. Can I simplify? Yeah, I sure can simplify a little bit. Even better. Yeah, well, already did that. Let's leverage it. You know, there's one more piece of simplification that we can do. We combine those two values that we have right in here, right? Something to the first power, something to the half power. When the two are combined, we get 3.5 power. Oh, okay. And now the electric field is along the y-axis. That's how we do it in a mathematical way. But that's the electric field. Remember that this is the electric field only along the y-axis. Okay? Along the y-axis. Whether y is positive or negative. That's the final solution of the net field in terms of Q, K, Y, and A. Okay, that's, okay, here you go. You can do the same thing for something else called the electric dipole. Okay. Everywhere else outside the y-axis, the mathematical equation is going to be more complicated. Okay, so you're not going to do that. It's lots of you can do it by yourself too. How does the electric field looks like along the x-axis, right? Along the x-axis, the solution is going to be much simpler than the solution along the y-axis. You can do that on your own. Okay. Oh, by the way, I predicted that the net field here at y equal to 0 is going to be 0, right? Let's double check if that's I got the same thing. Let's double check that. Here you go. We are going to go to our solution at y equal to 0. The net E field is 0 as well, right? We substitute 0 here in y, we substitute 0 here in y. 0 multiplied by something that's different of 0 is going to be 0. Okay? So we are double checking our equation from that analysis that we did before, that qualitative analysis that we did before. Okay? Field of 2-point charge, positive and negative. We can do the same thing for the dipole. And by the way, the dipole has a very important practical application. Why is that? Because some of molecules out there, they behave just like an electric dipole. It's the case of the water molecule. Okay, here you go. Positive charge on one side, negative charge on the other side. Okay, I'm gonna brush up very quickly because I want to start something else. The electric field along the y-axis is going to be an electric field that's going to point in this direction for the first charge, for the positive charge, and another field that's going to point along this direction for the negative charge. Along the y-axis, the electric field will be always in the horizontal direction, along the y-axis, the net field. Okay? And as we move away from the charges, the electric field should decrease in intensity. And if you do that, if you map, you can map too, right? You can map the electric field around this dipole. You're going to get those electric field distributions. Okay? Here you go. Well, we're not going to cover that. Let's skip that for now. We also have something else, electric field of a quadrupole. I'm going to skip that. That's for point charges, for a distribution of point charges. Now, something else happens whenever you have, so here you go. So far, we cover just the electric field, the net electric field, right? We cover the electric field of a point charge and 2 point charges. The procedure for 3, 4, n point charges is the same as outlined here. The only difference being the amount of work involved. So instead of dealing with just 2 electric fields, you have to deal with 3 electric fields, 4 electric fields, 5 electric fields, and then the equations grow larger and larger, okay? But the procedure is the same, but the procedure is exactly the same. Okay? What I didn't tell you, let me also brush up very quickly, okay? I did that for positive point charge, right? Let me just show you for a negative point charge. For a negative point charge, a single negative point charge, okay? Here you go. A positive point charge is the electric field is away from the charge, right? From the main charge. For a negative point charge, the electric field is towards the point charge. Okay? And that's the electric field representation, vectorial representation of the electric field. Okay? And I'm going to write it down. There are 2 ways. There are 2 ways of representing an electric field distribution. One, the vectorial electric field distribution with several arrows surrounding the charge distribution. Okay? 2 ways of graphically, I'm going to emphasize here that graphically, okay? Graphically representing the electric field distribution. But there is also the mathematical representation of the electric field, right? And so far I told you just about the vectorial representation. The vectorial representation of an electric field distribution with several arrows surrounding the charge distribution. And 2, the electric field lines. The electric field lines. This is a much simpler way of representing the electric field and requires much less work. Okay? Require much less work. And we have here, okay, here you go. Here's the vectorial representation of the electric field, right? Of a point charge, of a negative point charge. The other way is representing in this way, like lines that doesn't interrupt themselves, okay? Okay, here you go. Again, this is the vectorial representation of the field. Here's the line representation of the electric field. Instead of drawing several arrows, you just draw continuous arrows. If it's a positive charge, the arrow points away from the continuous arrow points away from the charge. Okay? And here, we already know that the magnitude of the electric field is represented by the length of the arrow, right? The length of the arrow represents the magnitude of the electric field. Here, the magnitude of the electric field is represented by the distance between the electric field lines. Okay? The further apart are the electric field lines are, the weaker the electric field is. Can you remember that? Okay? I'm going to write that down here in the notes. Okay? In the vectorial representation, comma, the shorter the arrow is, the weaker the E field is. Okay? In the linear E field representation, the further the lines are away from each other, the weaker the electric field is. It's far less work to represent an electric field in this way than representing an electric field in this way. Far less work. Okay? Here you go. Vectorial representation of the field. Line representation of the electric field. And we can have all sorts of different electric field line representation. Let me show you some examples for the electric dipole, for instance. We have 12 more minutes to go. Okay. Electric field lines. Okay, here you go. Isn't that? Oh, here you go. That's the electric dipole. That's the electric field lines of an electric dipole. Okay, do you see what's happening here? The electric field lines pointing away from the positive charge and points towards the negative charge. The higher the concentration, let's see if I can do better than that. Let's see if I can zoom in. The higher the concentration of the electric field lines, the stronger the electric field is. Okay? Nearby this charge, you have a higher concentration of electric field lines. Moving away from those charges, the electric field intensity decreases here. But as I move closer and closer to the other charge, the electric field increases. Okay? That here is the case of the electric field lines representation, not of point charges, but continuous distribution of charges. Imagine having an infinite number of electric charges very close to each other, negative electric charge very close to each other, and an infinite number of electric charges very close to each other, of positive charges, right? Very close to each other in this region. It's possible to prove mathematically and graphically as well that this type of charge distribution generates an electric field that is uniform. Okay? Let me copy that and put that in my notes. Right here. Capture, copy. Electric field line representation of my electric dipole. Okay? In addition to point charges, in addition to electric fields, point charge, we can also have the E field of a continuous charge distribution. Okay? Let's see if I have a drawing here for one of those. Point charges. Okay, I covered that. You can also look for the electric field line distribution of two point charges of same sign, okay? They have out there in the internet. Here for the dipole. Okay, and that's for the quadrupole. I'm going to skip that. The quadrupole is, okay, here you go. And now for the continuous electric field distribution. Let's see if I have an illustration. Oh, what a shame. I don't have an illustration of that. Oh, that's point charge. Let's go for the next one. We still have 8 more minutes to go. Illustration. Continuous charge distribution. See that? Electric field. Okay, here you go. This is the representation of a continuous charge distribution, a genetic. Okay. So let's say that we have a uniform. Let's say we have a uniform distribution of electric charges in this, in this strange geometrical pattern, right? So I want to know the electric field. Let's say I want to know the electric field at this point right here. What do I do? Okay, the way to do that is to get the contribution of each infinitesimal charge distribution of this object, right? There you go. That's the contribution of this infinitesimal charge distribution, delta P1. Let's, instead of, okay, I'm going to put it, instead of dq1, I'm going to put delta q1, okay? Delta q1. Here, the distance r1. Then we get the contribution of this other infinitesimal charge distribution, right? That's the whole idea. And then here we're going to have this contribution, right? Because this one is further away than this other one, then its contribution should be slightly less than this other contribution. This is a qualitative treatment, okay, folks? So you can have an idea of a qualitative idea how it works, how we do that in real life. Then we want the contribution of the third infinitesimal charge distribution, right? And this one is further away than the delta Q1, so it should be weaker than delta E1 and stronger than delta E2, right? And that's what we get. So that's the, let's make it a little bit weaker. Yeah, here you go. Delta E3. And then the net field is going to be given by the summation of all those fields due to all those infinitesimal charge distributions, okay? In this course, we are not going to calculate the electric field of this fancy electric charge distribution. It's going to should be too difficult to do that. We would need a computer to solve something like that. Instead, we are going to focus on some other types of charge distribution that are much simpler and has symmetry, okay? That's what you're going to do. And one of them is the plate distribution, a circular distribution, okay? One of them is a circular distribution, has uniform charge distribution. The amount of charge here at this spot is the same amount of charge here, and so on. A disk of radius r, okay? It's a problem that's easier to treat than that other problem that you saw. Along this axis, the x-axis, you can see clearly that the electric field is going to be pointing along the x-axis, because this infinitesimal charge distribution, this position, is the same as this infinitesimal charge distribution at this position, and their distances are the same. I'm talking about along the x-axis, okay? Just like we did for the point charge distribution. Okay, and the same thing apply for those other infinitesimal charge distributions here. So the net field of this distribution along the x-axis is going to be pointing along the x direction. Along the x direction. Okay. And by the way, this, let's see here. Oh yeah, it's a ring, okay? Don't forget it's a ring. Not a circle, but a ring. And another, another type of distribution that we are going to look at, let's document there so you don't get lost, right? Here you go. Continuous charge distribution. The most generic continuous charge distribution can be something completely arbitrary that is very difficult to calculate. See below, right? We have 2 more minutes to go. Let's see if I can finish everything that I'm going to copy this one right here. I'm going to copy this one right here. This one right here, okay? That's a very difficult problem to solve for the electric field, right? Copy. Here you go, see below. So we are not gonna concentrate on that. We are going to concentrate on some other geometries that are easier to deal with. The above geometry is much more difficult to deal pues mathematically. For this reason, we will concentrate on simpler geometries. Almost there, 1250, right? And what are those geometries? You know, one, ring, annular distribution, annular charge distribution. What else? One of them is the annular charge distribution. Another one, let's see, here you go. That's the annular charge distribution. The next one is going to be a linear charge distribution, right? Linear charge distribution. Okay. What else? We're going to concentrate also on the circular charge distribution. Circular charge distribution. Okay, we are going to look at the spherical charge distribution. Okay. Cylindrical charge distribution, and so on. All the above charge distributions are uniform charge distributions. Okay, and then we can stop here right now. I have office hours right now. Okay, if you want to hang around, I'll be here. Otherwise, I see you next Monday.
Thank you, Professor.
Welcome. Next Monday, we'll continue with the electric field, and hopefully we're going to get into the electric potential as well. We didn't get into electric potential today. We just covered the electric field, right? Electric field. Let's see. Come on. Welcome, Steve. I'm going to stop sharing here and stop my recording